Thank you very much for a kind introduction. My name is Semir El-Ahmar, and as you can see, I came to you from the same group and from the same place as the previous speaker. And I would also like to tell you about magnetic field sensors and magnetic field sensors for special tasks. In general, magnetic field sensors are a very universal sensor because they can measure or signalize magnetic field directly, or they can use magnetic field to measure many other quantities indirectly, like position, rotational speed, movement, and so on. This is why they can find many applications in many industry sectors. They can find application in magnetic drives, DC motors, various kinds of devices for process control, and so on nowadays. But none of these applications do not require from sensors to be, these sensors to be operational beyond a quite common temperatural range from -40 to 180 Celsius degree. This is a very common temperature range for operation for magnetic field sensors that are produced nowadays. What I would like to tell you today is a research concerning the use of specific materials, specific active layers for the construction of magnetic field sensors that can be operational and stably working in much wider temperature range, from cryogenics, from liquid helium temperatures up to 350 Celsius degree. That kind of magnetic field sensors are unavailable commercially nowadays. And this research goes against the constant development of the industry sectors in which magnetic field sensors are nowadays used very often, like automotive, like space, like military. I believe that expanding the thermal temperature capabilities of magnetic field sensors could be crucial for these sectors in future. Also, the very interesting aspect is the energy sector and the use of magnetic field sensors in future fusion nuclear power plants, but it was a topic of the last presentation, so I won't be focusing on that point. What is interesting, the research I will be presenting today and the research presented in the paper were conducted mostly using the infrastructure of our university and our division in so-called Sensor Lab, which is mostly a student initiative. I believe it's very worth to mention that. But let's go to the subject. If we would like to build a magnetic field sensor, we normally start from the fabrication of the active layer. The active layer is it's a main element of the sensor. It's an element that implements the physical effects basing on the sensor works. And after a few other steps, we usually end on testing the whole device and appropriate conditions to visualize this. Here you can see how this process looks in subsequent steps. You can see here the active layer fabrication and shaping the active layer using vacuum techniques, as well as optical lithography, shaping and fabricating the electrodes, also using metallization processes and optical lithography as well, fabricating a protective layer of oxides, as well as creating housing and electrical connectors and special binders that are appropriate for very extreme range of temperature of work for our sensor. And what we did, the whole device, you can see on the last picture, this is a finished device. Here on the other hand, you can see a block scheme of the sensor structure. It was shown during the last presentation. It's one of the platforms used there. We use indium-antimonide thin film as an active layer. It's heavily donor-doped indium-antimonide. We use tin as a donor because we want to expand or improve the thermal stability of the thin film. Normally, indium-antimonide is a narrow bandgap semiconductor, which is not optimal for fabrication of thermally stable devices. However, using appropriate and precise doping, we can virtually make a Hall coefficient almost independent on the temperature at some temperature range, which makes the signal of the sensor also quite independent on the temperature. Of course, it's not fully independent on the temperature, which we will see. And we use for this purpose a vacuum technique, a flash evaporation method. It's very unpopular method, but it's kind of variation of very popular methods in molecular beam epitaxy, which is nowadays used very often for fabrication. Yes, and to explore the limits of our sensor, of our structures, we performed a series of Hall effect measurements using a Hall effect analyzer that you've seen during the last presentation. Here, you can see how the handle looks like. So I can show you right now. It was the picture that was missing last time. And using this analyzer, we can create a temperature conditions, not only at a high temperature level of a few hundred Celsius degree, but also at low temperature level, down to liquid nitrogen temperatures, using a magnetic field of almost 0.7 Tesla, which is quite nice. Also, with the cooperation with the Institute of Low Temperature and Structure Research of Polish Academy of Science, we will be able to get access to the bitter magnets of the laboratory, and we will try to get even deeper in temperature, go down to liquid helium temperature, and go up with the magnetic field beyond 10 Tesla. But this research they are not performed yet. They are scheduled at the beginning of the next year. So the paper is not showing this research. I also can't show you today this research. But what I can show you today are a few things. Here you can see, let's say, standard dependence of the signal of our sensor, the Hall voltage versus the induction of magnetic field from 0 to 0.665 Tesla in both polarities of magnetic fields. It was a measurement made at room temperature at driving current of a single 1 milliampere, and you can see that it's a quite nice linearity of the signal versus magnetic field. Here, also the dependence of the signal of the sensor versus the higher supplied voltage of the sensor. And on the right side, this blue part of this graph shows you the answer of the output resistance of the sensor. So you can see that at higher supply, the sensor is still stable, which is very nice, because at higher supply, we can get also the higher base signal. And finally, this is the double graph of the basic electrical parameters of our sensor, Hall signal and sheet resistance, in a very wide temperature range from liquid nitrogen temperature up to 350 Celsius degree. Each of these parameters shows two courses, heating and cooling from room temperature, marked with blue and red. And we can get a few information from this graph. First of all, we know that our sensor is operational. It's in this whole temperature range, which is very good. And second of all, we can determine and have information about the thermal stability of our sensor, determining the temperature coefficients of these parameters. It was mentioned during the last presentation also. And we can see here that in a full range of operation from liquid nitrogen to 350 Celsius degree, the average coefficients of both of these parameters are less than 0.05% per Celsius degree, which is quite nice. It means that our sensor is quite stable. However, if we make this range a little bit narrower from cryo, which means here a liquid nitrogen temperature up to 200 Celsius degree, we can get these coefficients even below 0.01% per Celsius degree, which is extremely stable. And this could be the optimal range for operation for our sensor. To sum up, we developed a magnetic field sensor that can be operational from cryogenics temperature up to high temperature of 350 Celsius degree at least. We find the best temperature stability shown by appropriate temperature coefficients when the sensor is operating from liquid nitrogen up to 300 Celsius degree. We need more verification of the operation of our sensor in strong magnetic fields, as well as lower temperatures, which will be done. And we believe that this is a step forward towards development of magnetic diagnostic devices for broadly defined extreme environments. And here you can see exactly the same faces of people that you've seen 15 minutes ago, and those are people that were involved in this research or support our research in general. And thank you very much for your attention.